All right, welcome to episode 6 of Hoot, where we've been exploring different service mesh technologies. And in this episode, we are going to look at evaluating 4 of the different ones that we looked at. And I encourage you, and I have a link for it in one of the slides, to go back and look at the previous episodes where we introduce and get hands-on with some of these service mesh options. So I'll be your speaker today. My name is Christian POSTA. I'm the field CTO here at Solo. I've been involved in helping organizations move to microservices architectures for the last 5-6 years now. And I have a lot of experience in this area, including the more recent emergence of the service mesh technology. I wrote the first book on Istio, for example, and I'm writing a book right now, Istio in Action, for Manning. All of my slides I post to SlideShare. You can reach out to me on Twitter if you have thoughts or comments or questions. What we're going to do in this episode, like I said, is wrap up the series that we started at the beginning of the year, 2020. We're going to do a quick recap on what is a service mesh and whether or not you need a service mesh. And then we'll look at how they're generally built and architected, and then look at 4 specific service mesh implementations and look at some of the pros and cons or evaluation criteria that might be interesting to you. And then we'll wrap it up. Like I said, on the right-hand side, you can see a link to our YouTube channel, and there's a playlist there for the various service mesh options that we covered. We started off this year with Istio, and what we did in that episode was look at some of the newer features coming in Istio 1.5. And in episode 2, we looked at Linkerd. We did sort of an unboxing of Linkerd, getting started with understanding the different components and working through some of the examples from the docs. And we did the same thing for HashiCorp Consul Service Mesh, AWS App Mesh, and then Kuma from Kong and Maesh from the folks at Traffic or Containers. And then this is episode 6. We're going to continue our Hoot series with a different topic shortly, and I think we're going to be looking at gateways and ingress gateways and API gateways and that kind of thing. So let's get going. And just to set a little context, when we talk about the problem space that we're looking to address, we're looking to maybe go to a cloud architecture or microservices architecture. And when we do that, we have to build our applications with different assumptions than we did in the past, where maybe we're building 3-tier applications, or even in the original SOA days, where we would build services knowing that, well, we're going to build things highly available, things will never go down, things are fairly static. And in this environment, when we talk about cloud deployments, we talk about the assumptions changing and how the services that we deploy can go down and will go down, or appear slow or degrade and so forth. And so we need to build in this environment where the networking is not as reliable, where the platform is not as, there's no guarantees about that. And we end up trying to solve the networking challenge of how services talk with each other by overcoming those challenges. We end up seeing the complexity in our applications grow between the services, not necessarily just the services themselves. And when we go to cloud and we go to microservices, we're doing this for a reason. We're doing this to be able to go faster, to make changes to our different components in the system independently. And we've seen in the past through automation and so forth that we are able to go faster. We're able to deploy things faster. We're able to get things from get commit into production faster. But if we look at the bottom 2 metrics here in this table from the State of the DevOps report, we want to go faster, but we got to do it safely. We want to understand what's happening in our system. We want to understand steady state. We want to understand when things change. We need to observe the detail of of these services. We need to be able to lower the risk of making changes by slowly introducing changes into the system in a controlled way and doing things like canary automation and so forth. So when we talk about service mesh and some of the technologies to enable microservices within the context of the problem where there's more complexity in between our services now, we want to create an environment where we can understand what's happening between these services, lower the risk of making changes to the system, and ultimately move fast, but do that safely. So some of these challenges of deploying microservices applications into cloud native platforms like a Kubernetes or a public cloud include things like, how are we going to discover these services? These are potentially dynamic. They'll be changing frequently. They'll be failing at times. How will clients that want to interact with these services find them and do that reliably in a cloud environment? Things like retries when things fail, timeouts when things take too long, circuit breaking when we're noticing patterns of instability in one of the services that we're calling. We might not want to continue sending traffic to it. Routing between the services, controlling traffic at the request level so that we can incrementally release new features by sending just certain traffic to these new deployments. Being able to do health checking and request shadowing so that we can introduce new changes without impacting any production traffic. And logging and telemetry collection and distributed tracing and so forth. In the past, what we did was we implemented this in the code, in our application logic itself, or we would bring off-the-shelf frameworks that were designed for specific languages to implement these types of things. And as we moved from one language or framework to another, we saw deviations and differences in how these capabilities, solving for these capabilities, were implemented in the application code. So you might be using a JVM, you might be using Spring or Vertex. The paradigms are between those frameworks are different, and the implementations are different. Or you might be using a totally different programming language like Node.js. So now you have to go find the equivalent. What is the circuit breaking library for Node.js and client-side load balancing, and how are we going to expose telemetry and in what format? Maybe you want to use Go, maybe you want to use Python, or whatever programming language, right? So you have to solve these problems ideally consistently across all the languages, all the frameworks that you might end up using in your microservices environment. Now that creates a tremendous amount of burden on operating your services. For each permutation of language and framework, now you need to figure out a way to solve these problems consistently, and that's very difficult to do. And if you find that you're able to do it for a short period of time, then you need to upgrade and patch these libraries, and again, do it very consistently. Or on the other hand, you limit the number of languages and frameworks that you're allowed to use in your environment, and that might not be ideal either. So an elegant way to solve this is to implement these particular pieces of functionality out of process of the application, but deploy it with the application and allow any language and any framework to take advantage of things like client-side load balancing and service discovery and resilience, things like timeouts and retries and circuit breaking and so forth. So this is where the idea of a service mesh starts to come into play. The service mesh implements these capabilities and solves these challenges for you independent of language and framework. Now this all sounds really good, but before you adopt any new technology, you have to ask yourself, do I need that? Is my environment and my constraints such that I could get value out of adopting a piece of technology like this? Do you actually have a mix of languages and frameworks in your services and environment or your architecture? You might not. And maybe you already have some library-based ways of solving these problems and it works great for you. Then stick with it. Maybe you're going to Kubernetes and you're still new to Kubernetes and you know you need to solve these problems, but do you start throwing a service mesh into that equation? And I would say no. I would say get a good understanding of your existing infrastructure stack. Understand how you can leverage Kubernetes to solve some of these challenges. There is some initial support for things like service discovery and load balancing and resilience and health checking and so forth that you can get out of Kubernetes. So I focus on where you are in the journey to adopting this infrastructure, get the most out of what you have today, and then evaluate whether it makes sense to bring on new, potentially complex infrastructure to solve those challenges. Now, if you do run into these questions. There's a lot of different service mesh implementations out there. Who's going to support the one that you pick? Do they support multi-tenant or multi-clustered deployments? Do they support containers and Kubernetes as well as existing infrastructure, VMs? What is the operating model? Is it highly centralized or highly decentralized and so forth? So you're going to run into some of these questions as you evaluate which service mesh to pick and whether that's appropriate for you. So the service mesh architecture in general, like I said, starts with implementing those application networking features out of process of the application. Right? So we said the app can be written in Java or Golang or Perl and still communicate with the network through this service proxy. And the service proxy is where we implement the capabilities of the application networking. So if traffic's flowing through this proxy, we can control routing, we can enforce timeouts, we can do client-side load balancing and routing and so forth through this particular part of the application. So you can see here, I've drawn a box around the app and the proxy because they're treated atomically. They're one and the same. If the app goes down, the proxy goes down. If the proxy goes down, the app goes down. Right? They're treated exactly the same. Whenever the app tries to talk to any service outside of its boundary, it always goes to the proxy, and vice versa. Whenever any service tries to talk to this app, the traffic always goes through the proxy. Now you can do interesting things with this. If you have control over the proxies, you can configure them, obviously for routing and resilience aspects like circuit breaking. But you can also configure them to load certificates on both sides and encrypt the traffic and the transport between the proxies. You can capture telemetry and metrics, distributed tracing, and so on about what's happening over this transport. You can enforce policies on certain ends and certain sides of the transport and so forth. And this control plane component is what integrates the user or the operator of the mesh with the actual implementation or actually the enforcement of the mesh policy. So the operators and users are specifying configuration through the control plane, and the control plane is then pushing that configuration, those policies down to the data plane, which is made up of the various proxies that are deployed alongside an application workload. And from there, we can observe and understand the, let's say, request rates, the error rates, the circuit breaking events, retries, latency, and so on, about the communication, about the networking traffic that's happening between the services in this service mesh. So a service mesh typically provides service discovery and load balancing to the workloads in the mesh, secure service-to-service communication, as well as policy and intention-based based access control. We can do traffic control and shaping and shadowing and all, fancy things around the request. We collect a lot of telemetry and distributed tracing. And lastly, one of the most important things is it provides an API. The Service Mesh provides an API through which we can drive automation about doing things like canary releases or service debugging and chaos experimentation and so forth. So the API part of the Service Mesh becomes very important because you end up building things on top of it and you end up building automation on top of it. So let's quickly take a look at some of the existing Service Mesh implementations, some of which we covered in our series up to this point. So Linkerd is the first one that we'll take a look at. Linkerd is, specifically Linkerd 2, is an open source project in the CNCF and originally started by the good folks at Buoyant, now has a growing community. And Linkerd kind of kicked off this whole Service Mesh as we know Service Mesh today with their original release of basically they wrapped Twitter Finagle into a proxy. And Finagle was one of these, kind of like Netflix OSS, one of these libraries that implemented client-side load balancing, circuit breaking, and routing, and so forth. And they put it into a container and started deploying the container next to some of these workloads. Moving to Linkerd 2, they've improved the efficiency and lowered the footprint of deploying Linkerd. The control plane, as we saw in the previous diagrams, is in Linkerd's case written in Golang, while the data plane or the proxy level part of the architecture is written in Rust. They've continually been improving the feature set that they've been offering. The latest release is 2.7. And Linkerd's approach to the Service Mesh is, how do we simplify the installation, the operations, and the usage of the Service Mesh so that it kind of fades into the background while giving you a wealth of power and insight into what's happening over the network with as minimal configuration as possible. So Linkerd's control plane and data plane kind of breaks out like this, where you interact with the Service Mesh through CLI or through the web or through CRDs. And there's a nice user interface, web dashboard you can see in episode 2 of our Hoot series here. And you can do things like configure the proxy, you can pull telemetry back, put it into Prometheus, tie it into distributed tracing. You can, out of the box, there's always on mutual TLS and encryption of the transport, and you can configure the root CAs and so forth that generate the certs and sign the certs. Very good observability tools and being able to pull back they call the golden metrics or the top level metrics, including to be able to actually see the requests that are flowing back and forth over the system so that you can do some level of debugging. Some of the strengths of Linkerd, I would say very, very good experience when using it. It's, any of these service meshes are fairly complicated technologies, but I think the folks at Buoyant and the community around Linkerd has really set the bar pretty high in terms of usability and the experience of keeping you on the right path to being successful with the service mesh and getting a lot of value out of it. Right now it is Kubernetes only, so they're targeting only Kubernetes. And they're in the midst of working on multi-cluster support. It doesn't exist today, but it should be coming fairly soon. And I think there's opportunities to improve certain resilience capabilities like the circuit breaking and fault injection and maybe more access to load balancing or zone-aware load balancing and so forth that you might want. But overall, I would say even as early as probably 6-8 months ago when I did presentation similar to this, where their traffic routing and traffic splitting capabilities were missing. Those have been added, and Linkerd 2's feature set is growing to the point where you can use it as a general purpose service mesh. So definitely take a look at Linkerd 2. One of the other ones that we'll look at is Consul Service Mesh, or Consul Connect. And so Consul comes out of HashiCorp and was started a couple years ago now, back in maybe 2.5 years ago now. And what the folks at HashiCorp realized is, as people use Consul as a distributed key value store or as a service registry, that a lot of information about where services exist live in the database, in the Consul database, that you can layer on not just service discovery, but a level of policy and what services are allowed to talk with which other services, a layer of identity. So if we know where the services are and they register, then we can issue identity following the SPIFFE spec and so forth. That then from there, you can continue to build on top of to write routing rules and pulling back telemetry and so forth about the services that are registered and communicating with each other in what ends up becoming a service mesh. So Consul Connect, or Consul Service Mesh, is also just like Linkerd, I would say, is evolving and increasing its capabilities and its feature set. The latest release is 1.7.2. And actually, Nick Jackson from HashiCorp, and I just wrapped up a series on the service mesh for developer workflows using Consul Service Mesh. So we'll link to that in the notes, and I highly recommend taking a look at that. So Consul's deployment options are very similar to the generic service mesh architecture that I showed earlier, where you have a control plane and the data plane. In Consul's case, the data plane proxies, or the service proxies that we see here on the bottom, those are Envoy proxies. So we're using Envoy as the service proxy through which the traffic is flowing, and you take advantage and get the capabilities of Envoy in that case. The control plane follows a similar pattern, if you're familiar with Consul, in that Consul servers are a consistent database set. So they follow a raft-like algorithm to stay consistent, but then push out configuration to various Consul agents or clients that then cache the config and make lookups for the configuration very fast for locally running proxies. So for example, you might have a Consul agent as an agent on a VM with multiple applications and service proxies running on that VM, talking to the Consul agent directly and not going directly over the network for all of its configuration or certificate signing requests and that kind of stuff. So he talks as local as possible. In a Kubernetes world, this could be a daemon set of agents that run locally to a Kubernetes node, and any of the proxies that run on that node talk directly to that daemon set and so forth. So Consul is built, or Consul Service Mesh is built on a fairly known and fairly stable and widely deployed piece of software, Consul itself. And it brings L7 traffic control to those particular workloads that are participating in the mesh, solves for identity using SPIFFE, and policy or intention-based access control, and has capabilities for doing multi-cluster deployments and using Vault and other HashiCorp products that integrate nicely. On the other side, on the opportunity side, if you're running in Kubernetes specifically, it creates additional things that you have to manage. Right now, you have to manage Consul if you don't already, and keeping it highly available and keeping it consistent and all the parameters for doing that is not all that trivial. It does not use Kubernetes custom resources. It uses its own HashiCorp markup language or control language. And lastly, like Linkerd and some of the other service meshes attempt to be transparent to the app. HashiCorp Consul is not. The Consul service mesh is not. You have to kind of use the model that Consul has set forward, which is talking to localhost. And so if I want to talk to service A, especially in Kubernetes, I don't talk to HTTP service A. I talk to HTTP localhost on some port where I've mapped the ability to reach service A using Consul service mesh. So it's not as transparent as some of the others, but that does, the reason why they've done that is they've kept backward compatibility, and they understand that not every workload is going to run in Kubernetes, and you have to play nicely in both worlds. So Consul supports VMs as well as Kubernetes-based deployments. So Istio is another open source service mesh that originated in May 2017, came out of Google and IBM and Lyft, and others like VMware and Red Hat and Cisco and Pivotal and so on have contributed to it and helped grown the community, have even commercialized parts of Istio and support Istio. And as of now, 1.5 is the latest release. A lot of improvements around security or performance and architecture in that release. Istio is also based on Envoy, just like we saw Consul Service Mesh was based on Envoy. Istio is based on Envoy, and Istio's feature set is broad and very, very encompassing of all the different features that you can get out of Envoy. Now, on the other side of that, you have a lot of features and a lot of options that can bring complexity or perceived complexity. And Istio has been slowly iterating and improving on its experience. So far, the community is large. It's a large open source project. What the architecture of Istio looks like is, again, a control plane and a data plane. Control plane is a component called Istio-D that serves Envoy config through the Envoy XDS to the various data plane proxies, which again are based on Envoy. If running in Kubernetes, then you use the Kubernetes declarative approach to specifying configuration, and then Istio-D watches the Kubernetes API and pushes that configuration down to the proxies. Now, Istio does have some support for VMs and extending the mesh to those workloads that are not in containers and Kubernetes, but that is still evolving. Some of the strengths: so Istio is backed by a large, vibrant, open community, a large feature set, out-of-the-box ingress and multi-cluster support, and existing but evolving support for VMs. On the other side, things to improve, continued improvement on the documentation. There's been a big focus on iterative adoption of Istio components and features. I think that's going in the right direction, but it needs to continue. The illusion or the perception that Istio is complex is still out there and valid. Improvements to the installation and upgrade guides are coming along, but they still need improvement, and as well as performance. I think some of the more recent architectural changes will do a lot to alleviate some of the concerns around performance and overhead, but there's still work to do. The last one that we'll take a look at is AWS App Mesh. Now, AWS App Mesh is not an open source service mesh like the previous three that we looked at. It is available only on AWS, and what's slightly different about this one compared to the other ones is that the control plane components, so if we come back, let's look at this off to the right hand, we see that the control plane components, all of them, are kind of hidden or managed for the user. So as a user, you just worry about the data plane and getting the proxies into your workloads, and then using the App Mesh APIs to configure those proxies through the control plane that you don't touch or see or manage or have to worry about in terms of upgrades or any of the operating it basically. So it was announced a little while ago, went GA about a year ago, and a lot of the API supported by App Mesh is around traffic shifting and traffic routing and virtual, getting services virtualized in such a way that we can specify these rules independent of particular implementations. What's interesting about App Mesh is that it's supported across multiple deployment platforms. So if you're running in AWS, then running it in Kubernetes as well as non-Kubernetes is a solid option. So here's kind of an architecture, a little bit more of a drill into some of the API components in App Mesh. So a virtual node is the API object that we use to specify actual workload items, and then we refer to services and the rules that we can place around services as virtual services. And then we can specify routes and routing tables and routing rules in the virtual router that then the virtual service uses. Again, the proxy in AWS App Mesh is managed by the user, and you can use, there's auto injection components that you can use. And the proxy is also Envoy. So we saw Consul and Istio using Envoy proxy as the service proxy. AWS App Mesh does also. So again, App Mesh is built on Envoy, a managed control plane, so simplifies the operations of the mesh as a whole, supports multiple deployment targets like EC2, EKS, and ECS, and so forth. The API thus far has been kind of limited and skewed toward traffic routing and traffic shifting. That's improving. Just like any of these meshes, there's been a lot of improvement over the last 6 to 8 months in terms of what features get exposed and so forth. It ties in with the rest of the AWS infrastructure like CloudWatch or certificate management and so forth, and is free to use when you're on AWS. So a legitimate, you should be looking at App Mesh if you're running on AWS. Now, on the other hand, there's some of the capabilities that you would expect out of a service mesh, like policy enforcement and mutual TLS, don't exist yet. So there is an encryption that App Mesh supports, but not mutual TLS. It is deployed only on AWS. So if you're looking to deploy on premises or other deployment targets, that won't be a solid option for you with App Mesh. And then the control plane, although hopefully you don't have to worry about it, there is not all that much visibility into it. So now, depending on your use case, you might be looking at, well, how do I compare these? Which one do I use? And you might go online, might go on Google and try to find comparisons. And there's a decent number of anecdotal comparisons that you can use to kind of gauge what general direction you might be interested in. But at the end of the day, what we've seen, at least in my direct experience working either at Red Hat or now at Solo, working with users, organizations looking to adopt service mesh, the general direction is, start small, start with one proxy. So if you understand that the service proxies are deployed out into all of your workload items and the benefits of the service mesh come from as many workload items that are in the mesh as possible, that might be the case. But what we recommend is start with understanding the proxy. Start with adopting as little from the mesh that you can to get some value and get a good understanding of how that proxy works, how to operate it, how to debug it, and so forth, before you start sprinkling them out around your application architecture. A good approach is to take a ingress first approach. How do you get traffic into the mesh? Well, you need to solve that. But if you end up using technology that also uses the same technology as the service mesh, or so for example, Envoy, if you use Envoy as an ingress gateway into your cluster, into your mesh, you can get a lot of service mesh-like capabilities without going all in, again, sprinkling proxies all over the place. Once you get a gateway in place and you start to understand and operate your proxy technology that you've settled in on, then slowly introducing new capabilities, like maybe deploying the proxies to one workload and observing and understanding the challenges of doing that, and being successful with that, then moving to another workload, and so forth, until you start to grow your footprint. Now, we recommend, if you're looking at a VM and container deployment reality, look at things like Istio, look at things like Consul. If you're all in on Kubernetes and likely nothing else, definitely look at Linkerd. And then, of course, if you're in a cloud-specific environment like AWS App Mesh is you got to take a look at that, and then evaluate them for the things that are important to you, which might be usability, which might be feature set, which might be some of the underlying components that it uses, like an Envoy proxy, and evaluate those for performance and usability and so forth in your environment. Now, what we're doing at Solo, just a quick plug, is we're trying to simplify how you go about adopting these different technologies. So we've built an abstraction in collaboration with the Service Mesh interface community to simplify the APIs and unify the APIs across various Service Mesh implementations. So you're not worried about, well, on Consul, I'm doing HCL type configuration. On Kubernetes, I'm doing declarative language specific to Istio, and Linkerd doesn't have as much of that configuration surface. With what we're trying to do with this abstraction is make it so that you can deploy and configure any of the meshes that you want, and keep a consistent configuration set. And on top of that, if you can do that, then we can use something like, so the tool that we're working on, Service Mesh Hub, allows you to connect these different meshes if you need, or at least connect multiple clusters of a single mesh. If that'll probably be more likely, and until enterprise, the enterprise realities start to crop up, where you end up with more than one implementation of a thing. The Service Mesh Hub is a way to abstract and manage multiple different deployments and clusters of a mesh, including different types of mesh. So some follow-up and additional reading, I do recommend taking a look at the various mesh implementation, their communities, and the performance numbers, and the documentation, and the community notes that they've put together, including the roadmaps. Highly recommend that. And like I said, we'll leave some of these links in the notes. Reach out to me at any time on Twitter, or directly at my Solo email. I write about a lot of these topics fairly frequently, and I share all my slides and presentations on SlideShare. So that's it for me. Thank you for joining. Go check out let's see, that would have been maybe this slide. go check out the YouTube, the solo channel on YouTube. Check out the previous iterations of the series. And then what's coming up next is we're going to be talking about API gateways and ingress controllers, how those relate to Service Mesh, and how they compare to each other. So thanks again. Follow us at Solo on Twitter, and stay tuned to the next series.
Hang on a second.
Okay.